Chapter 17, we're going to turn our attention to thermodynamics. Which we start in the first semester when we consider enthalpy, or heat exchange, in chemical reactions. Now we're going to add another term, which is about the organization of the molecules. And finally, determine the total energy of a system and whether or not a process is going to happen spontaneously at a set of conditions. Here we have an example of a process looking at a car. In the forward direction, the car is decomposing. It's been left to sit out for some number of years, and there are chemical reactions that happen, and the formation of rust, and then things growing up and around it and falling out, and anything could happen. A storm could come along and hail and shatter the windshield. Right, this decomposing, if you leave a car outside in our environment, we know that this process of decomposition is spontaneous. It's going to happen. Okay, so let's define that. Spontaneous reactions occur at a given set of conditions. Without any outside intervention. Now, if we look at the reverse process, taking that rusted car and restoring it to what we would call factory, this would be non-spontaneous. Reactions cannot occur without outside intervention. So someone would have to get rid of the rust, paint the car, put the tires back on, put the windshield back in, shine it, take care of it. And so it's not going to look like this factory model again unless someone takes the time to do that. Something we need to point out is that spontaneous reactions do not necessarily mean rapid reactions. We have to consider kinetics or rates and thermodynamics separately. And we have a pretty good illustration here. If we're looking at the formation of diamond being converted to graphite, this is going to happen spontaneously, but it's going to be a very slow rate on the time of years. There's no outside intervention that needs to happen, but it's going to take a long time to go from one to the other. So this brings us back to the idea of the difference between kinetics and thermodynamics. Kinetics tells us about the speed of the reaction. Thermodynamics tells us about the initial and final states and whether or not something is spontaneous. So we're looking at the energy of the reactant versus the energy of the product or products, and whether or not something happens spontaneously. So let's define a couple of important terms here. Entropy, the abbreviation for entropy is S. Entropy tells us about the order of a system. So what we can say about entropy is that it increases with the number of equivalent states. How many different possible arrangements are there for a molecule in that particular system? If we're thinking about this in terms of order, we look at the difference between solid ice and liquid water. Okay, same substance, but in the solid form, if you look at the molecules themselves, they're arranged into this network. Very closely arranged, and they don't have a lot of energy. So this would be an ordered arrangement. Because the molecules are not moving very fast, they're not going to have a lot of different perspectives within that system. But when we look at the liquid state, we'll see that they're no longer arranged into that grid-like lattice, that the molecules are moving more because they have more energy. And they are more disorganized. So we would say that the entropy increases. Because there are more arrangements for the water molecules at the liquid phase. The second law of thermodynamics states that for spontaneous processes, the entropy of the universe increases. So if we're thinking about initial and final states, we would call this delta S for the change in entropy. And this is going to be, for the universe, this is going to be greater than 0. Let's take a look at this process related to water and talk about the entropy of the system. We can write the reaction. Water, liquid, goes to water, gas. Okay, so that's writing the reaction. Now what is happening to the entropy? If we look at our box here for the liquid, I have many more molecules in that defined space. As a result, there is more restricted movement. As compared to the gas phase. It's all about perspective. What are we comparing it to? Are we comparing it to the solid phase or to the gas phase? Then when we look at the liquid, the gas phase here, there are fewer molecules. And they are much more spread out. So there is more movement as a result of or causing the difference. So we would say that entropy going from the liquid to gas phase, entropy increases. Let's look at another example. In this case, we have the solvation of sodium chloride in water. So we write the reaction first. We're going from sodium chloride solid to sodium chloride aqueous. We don't have to write the water as long as we put aqueous as our phase there. Okay, so we dissolve this in water. Salt begins, NaCl is in an organized crystal. Matrix. With the sodium ions are our purple ones and our chloride ions are our negative one. They're going to be organized in a repeating fashion. And so on. When this is dissolved in water, what happens is that the water pulls apart the individual ions. Remember, we've got a little bit of negative on an oxygen, a little bit of positive on each hydrogen. And so the hydrogen is going to be attracted to the chlorine because chlorine is going to form a negative ion. And the oxygen is going to be attracted to the sodium. And it's going to pull it apart. We're going to ionize this substance. Individual ions Na plus, chloride negative. And you can see this represented here on this top picture. With our sodium ions being surrounded by the oxygen, you can see the red of the oxygen molecule there. And our chloride ions being surrounded by the hydrogen, the white portion of the water molecule. Right, when we consider order of this system, sodium chloride is going from a highly organized crystal to separate ions. So in this particular case, it's becoming more disorganized. And so entropy increases. The randomness of the system increases is another way to think of that. Randomness increases. There are more possible arrangements for each positive and negative ion in solution as opposed to in the crystal. Now let's take a look at a couple of example problems. First one, which of the following processes are spontaneous? And you're just assuming average conditions, unless you're told something else specifically. The combustion of natural gas. Okay, so what this means is we have the reaction CH4 plus O2 goes to carbon dioxide and water. And if we light the oxygen, the methane, we mix those two together. So what's going to happen, this is assuming that this process is going to happen. So for this one, we would say delta S increases. Whoops, that's not what I was asking about there. So we would say that this process is spontaneous. The fuel will burn as long as I spark the oxygen and mix it with the methane. The second example, extraction of iron metal from iron ore. This would take a chemical reaction, something to pull that metal back out from a mixture. So we're going from a mixture, which is the iron ore, to a pure substance. This is not spontaneous without some sort of outside intervention. We're going to be purifying something, and so that takes some work either by filtering or by distilling, by some process. Right, the third example, a hot drink cooling to room temperature. If you set a hot drink out, it is going to cool off. It is going to come to equilibrium with the environment, so this would be spontaneous. We don't have to do anything to it. The warm body is the hot drink, and it's going to lose heat to the environment. The next example, drawing heat from the ocean surface to power a ship. I'm having to convert thermal energy to electrical. And this transformation would require some sort of outside intervention, so this process is not spontaneous. Right, so to answer our question, which processes are spontaneous? The first one and the third one. In our second example, we're going to predict the sign of entropy for the following reactions. And I have to go back in here and put in my arrows. So we want to know, is the system greater than 0? That is less organized, going from reactant to product. Or is delta S less than 0, more organized, going from reactant to product? I can also think about the moles of gas and the product side. If moles increases, moles of gas increase, delta S is going to be greater than 0 or positive. If moles of gas in our product side, if this goes down, then delta S is going to be less than 0 or negative. Another way to look at this too is if I'm going from one reactant to two products, or in this case, two reactants to one product. The last one, we've got 4 reactant molecules and 2 product. Okay, so our first example here, we have 2 potassium chlorate solid going to 2 potassium chloride plus 3 moles of oxygen. So on the reactant side, there are 0 moles of gas, and on the product side, there are 3 moles of gas. So in this case, delta S is positive, greater than 0. All right, our second, we have sodium solid plus half a mole of chlorine gas. So that's half mole of gas. Go to form sodium chloride solid, 0 moles of gas on the product side. So this is decreasing, and that would be negative, where delta S is less than 0. Our last one here, we have 4 moles of gas going to 2 moles of gas. So again, this is decreasing. Moles goes down, and so the change is negative. You're going to work a couple of problems like this on the example set for the first section.